I'm working on that. It's a green. It's try and turn the projector off first.
Hold it for like 3 seconds.
Yeah.
Right.
Yeah. Hold that. So, what are things that you feel like you need to understand better? Some things we went through fast.
Understand with the goal of we'll discuss it in our breakout groups, or understand with the goal of there are things we need to decide and we don't know the answers yet.
I think understand better in terms of like what the effort is trying to do or how things work. At least there was a suggestion for some discussion on that. Or a big picture.
I think I'd like to understand the big picture of the Smirky a little bit more.
Okay.
The development of atom or types, rather. Development of force types.
Right, right. Specifically the chemical transformation part of it.
Like how it makes moves? Or what the goal is?
Right, yeah. So understand the Smirk's pattern matching, the overall strategy of the Smirnoff force field. And I think I'd like to understand better what the role of the Smirky rules for chemical transformations.
Proposals, I guess.
Okay. Some of these we might take right now, some of them we might punt. What else? Anything else?
I'd like to understand a little bit more about when it comes to the optimization, what happens with tricky things that can't be fit without big trade-offs, and at some point, is there some manual intervention saying maybe the experimental data isn't worth fitting, or maybe you just make a decision, okay, that experimental data point can't be right because some sort of error, and it's been throwing the thing far away from good parameter space because someone entered 999 into a database. And
one good thing about this database is they've done a lot of that analysis already. There's
Okay.
a lot of different ways to check it.
Yeah.
And everything comes in, they check it just to see is it consistent or inconsistent.
Yeah, that's good for NIST. If we put in other stuff, though.
Can you
Yeah.
use the same principle though? Like they basically build models to hold the data.
Run the same analysis.
But they use simple physical property extrapolation models. We want to do something more than that, but we can still use the same philosophy of trying to flag data sets that are inconsistent.
Yeah.
How do we, this is part of it. How do we
Flagging
flag back
inconsistent
data? So
data,
I'd like to
incompatible
understand
data.
how do we do that in a Bayesian framework
Right.
too.
That's a better representation of my question.
I would say inconsistent or incompatible data. It may not be bad. It may just be
Right.
inconsistent.
Right.
Anything else?
The practical implementation of RJMC, particularly when you're changing from one model to another, getting good transitions, your parameters.
I'd like to hear more about the free energy guided optimization. And I think we're reserving some time in the morning also for more about the QM database effort that
Yeah, Daniel's going
Daniel's
to talk a
put
little bit about that.
Yeah, on this, from an engineering side, I kind of like to see like a plot of how, all of your core modules actually link together and what they are and what they should do. So some sort of like overall plan for that.
If such a plan exists.
Or perhaps make one in that case.
Okay, anything else?
One thing I'd like to make sure we discuss is like what all the needs from a QM database might be, so that we make sure that whatever we build is going to serve the research purposes.
And on that, you might want to figure out if you just want to build a database for yourselves, or if you want to see if you can put in 10% more effort and have a database that the AI and ML guys will contribute to on top of reaction work guys. Because there's no general framework like that out there, and aggregating data, everybody can use it.
Yeah, I mean, I think we'd like to do the latter if you can tell us what the 10% more effort is.
Yeah, I mean that's the trick but it's worth, I think, at least trying to explore that a little bit.
Yeah.
So generally, would it be
We asked the machine learning community that question.
Yeah, so like I said, we could we can contact you with Gas or Alan or Bill Dallas, I'm sure.
would it be like what could be deliverables or external modules besides the force field itself? So say someone didn't want to use the force field itself,
yeah.
but liked all the property calculation stuff. Could that be? Is the plan to have those things completely decoupled and not dependent?
I think right now the idea is to put the generally useful tools in the toolkit so that you can get all of the toolkit, provided it's not enormous, right? But if there's several things that would make sense to stand on their own and be maintained separately, we could totally do that. But I think the goal has always been to not, like, if there's something that's useful on its own, you should be able to use that on its own.
So organizing.
We should also discuss any final changes to the Smirnoff format before it's.
Okay, so I think part of what we should do, like overnight, is put your name down at the bottom of the doc if there's any interest group you're particularly interested in, or there were some notes sort of above that in the agenda section on interest groups we might have. So take a look at those and the ones that are actually at the bottom of the doc with some names by them, and assign yourself to one or more of those, and then that'll assist us tomorrow when we're trying to organize people and start making plans. But clearly we're going to have a group that needs to go off and sort of discuss QM database infrastructure and things. The way I'm thinking part of tomorrow is going to work is that we're going to have like breakout sessions where the groups go off and discuss, and then kind of come back and update the whole group on what they're thinking, and then the whole group gets to say, well, wait, but did you think about this? And then they go off and discuss it again and come back. Looping.
I think the potentially important thing for us to discuss at some point is what is our, what is our like first valuable product going to be? What are we going to use to convince our industry partners to continue funding us?
No, they have to start from
Sure.
Yeah, in some sense it's, well, we need to use something. I think the answer is, well, we're going to need, the first step is going to be use something like force balance to refit some of the parameters and show that it's improving accuracy for properties X, Y, and Z.
Sure.
Which I think shouldn't be that hard, but we still have to know how to do it.
Probably going to be the torsions, right?
That's what the industry people would care the most about.
Mm-hmm.
There's like the single one thing.
The torsional potentials?
Yeah.
Or torsion.
The torsion parameters.
The torsion. I go back to the issue that those are not independent and non-bonded, so
But, I mean, we would refit them in the context of everything else.
of non-bondeds that they're using already.
Yeah, I also kind of worry that, so I agree that that's like the biggest thing, but I also worry that it's perhaps harder than some of the other things.
The torsions?
Yeah.
What are the other things that are
Like, for
easy?
example, Leonard-Jones parameters would be, I think, easier to refit. At least selected Leonard-Jones parameters.
But my concern in a way is that
Mhm.
that makes sense to me because we have to subtract out the Leonard-Jones terms before we fit the torsions.
Yeah.
So if we generate torsions and then we change the Leonard-Jones, we have to go back and
Yeah, well,
Oh,
that's,
no,
that's
we're
partly
always gonna
that's
have
the
to go
plan,
back
is
and do
we're going to
everything.
be each. Well, like the first refit of the torsions is going to involve automating refitting the torsions.
Yes.
So then when we refit the Leonard-Jones, we
You'll
just refit the
automate that
torsions
as well.
again.
So, but the first go round would be in the context of what Leonard-Jones parameters?
I think it would be given the Smirnoff 99 frost. Start with everything else the same except for the torsions and maybe the valence terms,
Okay.
and just start to improve those a little bit because that's going to be the most gain for the least amount of optimization effort, right?
So, yes, and furthermore, the non-bonds, so the one for electrostatics, the one for Leonard-Jones.
Yeah.
Those are actually right now in Smirnoff, they are absolutely identical to what's in
Right.
Parm 99, Parm 99 Frost, and
Yeah.
probably GAF before it got force balance.
Yeah.
Okay, so those are the most similar, the most acceptable, the most canonical.
Right.
It's the torsions at the huge collapse in redundant parameter
Right.
space happening with the valence angles and the torsions themselves. So where I am most likely to commit my worst sins in collapsing these things
Do tell.
down is in the torsional parameters where I was taking many chemically similar torsions,
Right.
assessing if they weren't very different. I'm saying Smirnoff 99 Frost is a starting point, so I erred on the side of simplicity.
Yeah.
The other thing is it's likely that Permafrost, from which I made Parm 99, Smirnoff 99 Frost, we are likely to have, had some defects in our hypervalent sulfur and phosphorus torsions. Now, some of these, Caitlin has come in later on and kind of done a franking force field with some GAF parameters in there. So where we have most likely made the biggest, having the biggest problems where we could get the easiest wins is actually in the torsional term because the 1,4 component of it is actually probably canonical.
Yeah. No, I see. I think it sounds great, actually. I think you're right.
So
if you start with Smirnoff and whatever and optimize the torsions, then you can also use these kinds of quantum energy minima to see, do I do a better job replicating?
And in parallel,
important-
we can get the Leonard-Jones stuff going so that it can be brought in more
Absolutely.
cheaply into
Yeah.
Yeah, that's
So
what
in
makes sense.
Leaping, you have basically torsion fitting stuff in force balance we can
Yeah.
repurpose for this.
Also, it will be easy to convince the industry partners that we're doing. How do we convince them that we're doing better? All it takes with torsion parameters is comparison to the QM torsions themselves.
Yeah, that's a good point.
Right,
Yeah.
so if they can
So-
throw us some molecules that they found were problematic that they can share
We
with
could
us,
just throw them
we-
into the-
we can do the high level thing and show that we get much better agreement with the super duper quantum for finding the key conformations. I think I would like to have that for drug design. I think that sounds really valuable.
I wonder for folks in the industry who have done this before, what is the quickest way to show them that we've done a good job? Is it like two-dimensional heat maps of energies that are most convincing, or are they like scattered plots of R squareds or?
Yeah, actually, I think they'd be probably pretty open to different kinds of data, what kind of graphic you show, but I think the data they need to see is that, the before and after picture of, the force field expression of these torsional potentials was deviated with respect to QM potentials by this much before and only this much after. And Schrodinger got much more mileage than I thought they should have gotten by just cherry picking certain pathological cases. But we could do that, and then we could also show the more compelling aggregate measures.
Are there crystal structures where the small molecule, somebody had to do something fancy to get the small molecule to work? Because you can show that when we use the correct force field, the small molecule pucker and these two congested groups are in the right conformation, whereas if you use the baseline model, they're not. I mean, that way. It's a crystal structure, even not just QM.
Yes, and so we just have to be a little nervous then about crystal structure artifacts, like tendency to force aromatic pendant torsions to go planar.
But that's an artifact of the force field, right?
No, it's an artifact of the crystal pendant. If you get much higher symmetry, if you go like 0.2 or 0.4 of a kcal up the torsion barrier, but you get a beautifully symmetric crystal, the lattice will make you do that.
Interesting.
You can see in the CSD, when you look at the histogram, you see something that should go like this, and it goes boop, and that's because of it's at 0
I guess
or 180.
what I have in my mind is really something that I think you said when we met up at Irvine one time, which is that, and maybe it's related to MMFF as well, which is you want the different groups gearing together to give you the right confirmation preference. Are there some showcase examples?
Yes, indomethacin. Yeah, there's some cases that I know about just because they're in my own war stories. But Pfizer will have their war stories. Our industry partners, what we should ask them to do is not tell us, keep us blinded with respect to their pathological cases, and then try them on before and after Smirnoff.
Sure, yes, but we want to hear about the pathologies that remain afterwards, right?
Absolutely, but I mean, what we're discussing here is what our first deliverable would be. I'm proposing that during these torsions, the way they're going to actually see if we're up to snuff is they'll be comparing to their own favorite QM potentials for their own favorite pathological cases. I think Mike is right. They will actually haul up the crystal structures, and within crystal lattice symmetry artifacts, we should be able to see improved performance, or else we've got to ask ourselves why we're doing this.
A lot of them are also very interested in free energy calculations. So Levi has been working on compiling some public data sets. Some of them come from Merck that have been disclosed in publications, Merck Kiga. Some of them are like the JAX set, for example. So we're slowly working our way up to be able to do these same free energy calculations. Already we've got a little bit of a benchmark with the CMET diverse scaffold data set with GAF. I think I showed you this, or GAF2. It's like 1.2 kcals per mole or something like that. So if we can do better than that on a free energy calculations too, then that's clear demonstration that we're moving in the right direction.
I'm just not sure that that's as low-hanging fruit.
No, it's not a low-hanging fruit, but it's going to be
getting the non-bondeds right. So I was just thinking if we just want to show the torsions.
The torsions are much better, yeah.
Yeah, as an early.
That's a good point.
Great.
And to be fair, we're actually starting from the docked crystal structure, so we're skirting a couple things that we're not starting from just random location in the simulation box.
For the free energy.
For the free energy
We
calculations.
have to wrap up for dinner. I just wanted to say one last thing about this. This first deliverable is refitting selected torsions, so it's not refit all the torsions.
There's
Part of
only-
how we make this bite-sized is we chunk up chemical space.
How many torsions are there, though?
It's still a little clear what the subgroups are, because these are like distinct questions. That a
Yeah,
couple
this
people
is
have
just stuff people want to understand that we might get to at some point.
Did you see the document?
We're going to work
There are
on subgroups in the
They
document.
propose subgroups.
And we need to work on